computer. And hello, everyone. Welcome to today's IBM seminar. My name is Peng Mingguo. I'm a postdoc working together with Professor Disha at Western University. Today, it's our honor to invite Dr. Yan Zhang from North Dakota State University to give a talk about multi-scale studies of physiologically and pulsatile flow and cardiovascular hemodynamics. I need to mention that today's talk will be recorded. If you do not want to show your face, please just turn off your camera. Before the talk, please give me 7 minutes to introduce our guest, Dr. Zhang. Dr. Zhang is an associate professor of mechanical engineering at North Dakota State University. Before that, Dr. Zhang worked as a postdoctoral researcher at Western Michigan University for multi-physics modeling research. His research interests include biofluid dynamics, experimental aerodynamics, wind engineering, and advanced flow visualization. Over the past few years, his work on various cross-disciplinary projects have been funded by various agencies, including AHA, NRH, NASA, US DOT, EPA, Air Force, and Navy. Dr. Zhang served as editors and reviewers for many journals, and also as review panelist for multiple NSF NASA grant review panels. Now I will give the floor to Dr. Zhang. Welcome. Wait, you are mute. You are mute.
Can you hear me now?
Yeah.
Yeah, okay.
Thank you.
Let me share my screen again. All right, again, thank you very much for your introduction. It's a great honor to be here to present some of our research on multi-scale studies of cardiovascular hemodynamics. Again, my name is Yan, and I'm an associate professor at North Dakota State University. Just a little introduction to our university, in case you don't know. I believe many of you don't know where we are. We are located right here at the border between North Dakota State and Minnesota State. So we are just at the border. We are in the Red River Valley. We are one of the two major public university in this state, and we have a history about 130 years. Currently, we have an enrollment of 12,000 students, and we are also only R1 university in this state, meaning that we're the biggest research university in the state. So our university is very famous not only for academics, but also for sports. Our Bison football team is a champion for many years recently. So they're a very good athletic team. And also we're located in the city of Fargo. You might have heard of this name from movie or TV show, but it's not actually the picture of the Fargo. So it's actually shot in Minnesota State. But yeah, the city of Fargo is pretty nice place. So we're the largest city in the North Dakota, and Fargo, Moorhead, and West Fargo area is like 250,000 people. It's like a medium-sized United States city. And because our state also have the Bakken field of oil field, so the second largest in the United States. So it's pretty fast-growing economy. So the city has a lot of company either headquartered or have a branch in this city. So the job opportunities are really good. So yeah, in case any of you want to visit us, welcome. If you have any students, if you are a student who want to study in our university, also welcome. So we're a very nice city. We're a little bit cold in the winter, but summer is really nice. We have access to many state parks and national parks in the state. A bit about us, our department and lab. So we are College of Engineering, Mechanical Engineering department. We have 18 faculty members and 600 plus students. We are one of the biggest department in the university. And myself and another colleague of mine are co-directors of Advanced Flow Diagnostic Laboratory. We have, all the major research capacities that allows us to do fluid dynamic experiments. So we established 2 research wind tunnel since we came here, one closed, one blowing wind tunnel. And we also established a hydrodynamic tunnel for swimming robotics and fish swimming hydrodynamic study. And we have supersonic and hypersonic nozzle testing apparatus. We also have many high-speed optical measurement systems, including tomographic PIV, PSP, LDV, Schlieren, and all these equipment are available for different kind of research. So our projects are supported by multiple different funds to do multidisciplinary research, including cardiovascular hemodynamics, wind turbine aerodynamics, and erosion microfluidics. So in this talk, I'm going to focus on some of our work on cardiovascular hemodynamics. So as this picture shows, the cardiovascular system is really, really sophisticated, and the fluid dynamics in it is really rich phenomenon. So it covers a wide range of Reynolds numbers, from very, very small microcirculation to up to 10 to 1,000 ranges, like in the really large aorta and artery flows. It can get too turbulent. So also it involves a lot of nonlinear fluid structure interactions, such as aortic valve, heart valves, vein valves. There's a complex interaction phenomenon. And also it involves a complex physiological background, as we will show later. So it requires a multi-scale, multi-dimensional, multi-platform. Okay, so it requires a combination of different aspects of efforts, like computational, clinical, and also in vitro experiments to understand all the problems. So the research method framework for this field is normally can be illustrated like this. So a problem in the clinical data suggests a problem, and we can use experimental and CFD tools to study the local flow details and fluid structure interaction. For example, for implantation of aortic artificial heart valves. So normally patient-specific CFD simulation can be conducted first to examine the hemodynamics before the clinical surgical implementation is taking place. So that was very helpful. On the other side, there is also system level simulation, mainly based on lumped parameter models, which can involve physiological responses. So consider thinking this human body as a whole. So it also can include very complex physiological factors that cannot be studied by experimental and CFD study. So in the meantime, system level simulation can also provide initial and boundary conditions and with physiological relevance to experiments and CFD. So that is also very helpful in terms of providing waveforms of pressure and flow, and also the boundary conditions. So in this talk, I'm gonna just separate this talk into 2 parts. The first part is some of our work on the system level cardiovascular hemodynamics, basically based on the open source, modified open source lumped parameter model. And then we will talk about 2 applications that we published in the recent years using this model. And then we're going to focus on local hemodynamics experiments. So we're going to introduce the method that we're using, the setup we're using, and also then talk about a couple of experimental results for aortic valve hemodynamics, aortic arch, and also the left atrial appendage flow. So first part is a lumped parameter model. So we're going to talk about the system level hemodynamic responses to different kind of external disturbances. So first of all, the lumped parameter model is really simple down to the fundamental level. So if you consider the human body as a combination of different parts, different compartment, then we can model each compartment using a electrical circuit analogy. So that's a fundamental idea here. So this kind of unit, we call it Windcastle model. So this is really based on the idea that the blood flow is mainly Newtonian. Okay, so we don't consider the non-Newtonian fluid, which is true when the flow rate is, the shear rate is greater than 100 per second. And also we consider only the laminar flow effects. So you can see the pressure drop is a linear function of flow rate as in the normal pipeline. So then we can actually replace the pressure drop with the electrical voltage difference, and the blood flow then is replaced by the current. And then the viscosity and radius and length is all involved in the resistance. Okay, so that's the fundamental idea. So then using this idea, then we can change the cardiovascular compartment into electric circuit units, which is we call it Windcastle units. Okay, so normal Windcastle units consist of a couple of pressure nodes. Okay. So here the PN and PN minus 1, PN plus 1 is the pressure nodes representing the blood pressure at different location of human body. And also the resistance in between representing all the parameters involved here. And then the capacitance is basically representing the compliance, okay, how much the volume of the blood can it store with a certain pressure change. Also, of course, you also have these pressure outside the blood vessel, which is the interstitial pressure, which is outside the blood vessel. So it controls how much of the volume it can change during a pulse of heart pulse. So if we build this way, then each of the Windcastle unit, we can build an ordinary differential equation like this. And then if we consider this human circulation at this, we can segregate in this whole circulation into different compartment. Then we can combine them together to build this closed circuit model. So this is built based on an open source code developed by MIT back in 2002. So this one consists of 21 Windcastle compartment. So for example, here you have the upper body, veins compartment, microcirculation, artery, etc. So and a lower body, abdomen, and different organs that is important. So all of these resistance and capacitances are all based on the physiological clinical data from literatures. Okay, so all of these together, we have 21 compartments, meaning that 21 ordinary differential equations. Then we can solve it using Runge-Kutta method. And of course, there's more details related to it. We're going to talk about it in the next few slides. So here we need to pay attention to some of the most important circuit here is first is the heart chamber. So heart chamber and also lung compartment, and also the microcirculation and vein compartment. Okay. So the heart compartment, because the heart is such a unique compartment. So it has 4 heart valves to control the one-dimensional flow. So we use diodes to regulate the one-dimensionality of the flow. And in the meantime, the heart is an active organ, so it contracts, and the elastance and the compliance changes over time automatically. So due to the muscle contraction. So we also need to model that compliance change as a function of time. So here the compliance is replaced by a function that fitted from the experimental clinical data in this model. And then these 2 valves representing here, for example, the left heart representing the mitral valve and also aortic valve, controlling the one-dimensional flow. So also the other unique compartment that we need to pay attention is the lung, also vein compartment, because it represents the nonlinear pressure and volume relations. So for all other compartments, we can model it as a linear resistance, because it's non-changing, right? The resistance is not changing too much and it's changing linearly. The pressure and the volume is changing linearly. But for veins, because of the vein nature is very thin-walled tube, it's collapsible. So once the pressure inside and outside, the transmural pressure changes, the cross-section will change non-linearly. So for example, as the transmural pressure decreases slightly negative, that means that if the pressure inside is slightly smaller than the outside, the vein will collapse into a ellipse shape and then dumbbell shape. So you can see here the pressure decreases in a nonlinear way as a cross-section area changes, as the pressure changes. So we have to model that using more nonlinear equation like this. Okay. On the side notes, we are actually doing currently doing some research related to the nonlinear fluid structure interaction in the collapsible vein. Some of the results we're showing here, like we're investigating what is happening. Okay, so why you're changing the transmural pressure between the internal and external space at different Reynolds numbers. You can see we replicates this thin-walled tube, replicating the vessel, the vein vessel fluid structure interaction. You can see the pressure decreasing slightly negative. We have these collapsing area, cross-sectional area. And also we found that as the Reynolds number increases above a certain critical Reynolds number, it started the self-excited oscillation, which is well-known phenomenon in the Starling resistor. So while you have a pressure dropping, it started this kind of self-excited oscillation. Okay, so going back to the model, a cardiovascular system model, another unique feature of the system level simulation is that we can consider the human body as a really complex physiological system. So one of the features is that our body has this short-term control system. So for example, if you are, the blood pressure is under certain situations, all right, so we have these sympathetic and the parasympathetic signals that can control our system to adjust the blood pressure, either going up or going down, right? So, so for example, in flight and fight situations, which for example, you become nervous, right? So then the autonomic nervous system will actually signal the sympathetic nerve system to give a plus signal to increase the heart rate and also contractility and the resistance of the arteries and the venous tones, so that you can adjust the blood pressure accordingly. So then under other situations, so the parasympathetic signals will be activated. So then it will be opposite, giving the signal to decrease the heart rate and also resistance and venous tones that change the blood pressure in the opposite direction. So in the cardiovascular system model, we also consider this as a set point control algorithm, and also based on the clinical data. So overall, by solving these 21 equations and also all these physiological data and the control system, and we are able to generate a realistic physiological output from the CVSIM model. So here is an example of the pressure waveform we generated for different pressure nodes, including left atrial, left ventricle, and the systemic artery and the venous pressure. So you can see that representing the pressure wave pretty well. It can generate a beat by beat in hemodynamics at all different locations, and also in time scale of seconds. And however, it does not have a long-term effects, and it does represent a closed fluid system. And there's no input and output. So later on, we will show that we modify the system to study different kind of physiological problems. The first example application I'm gonna talk about is the digital astronaut projects. So this is a project we got funded from the NASA AppScore funds to study how the astronaut, how a person's hemodynamics factors, hemodynamic parameters can change, and in the microgravity exposure for a very short time, and also the effectiveness of the countermeasures to counterbalance these the changes using a numerical model. So we're using that CVSIM model to simulate this kind of short-term effects. So as we all know, the astronaut go to the microgravity environment. So the blood will actually shift upper body towards the upper body, toward the head, because there's a lack of a gravitational pull, right? So under Earth gravity, the blood pressure in the legs is actually much higher than the heart level because of hydrostatic pressure gradient, and in the head is much lower than the heart level. So, but in the microgravity, the gravitational gradient disappears, so the pressure is actually more uniform. So it results in the blood shift from lower body to upper body. So this can cause a lot of different problems, including the puffer face blood. The face will look really dilated, and also impaired vision because the blood will pull in the eyes. Also orthostatic intolerance when astronaut going back to the Earth's gravity, they cannot stand up because the blood pressure cannot go back to the head immediately because of that adaptation. So currently, countermeasures such as lower body negative pressure is a measure that proven to be effective in space station. So the astronauts trying to use the lower body chamber as an exercise to try to restore its blood pressure hydrostatic pressure gradient. So we kind of want to use the CVSIM and extend this model to simulate these kind of effects. So what we do is we kind of do some modification to the CVSIM model. The first modification is we added the hydrostatic pressure gradient terms to each of these compartments. So you can see the green arrows representing the gravity working, helping the blood flow in the direction of the flow, and the red arrows representing the blood flow, hydrostatic gradient that works against the flow. And that's the first change. The second change is that because in the blood shift, there's also significant blood filtration through the micro circulations. The blood more water between the internal and intravascular and extravascular fluid exchange will happen in terms of under gravitational change. So we kind of modify the normal microcirculation compartment to including the interstitial fluid compartment, which is a lymphatic system. So we kind of added these units into the system. So here is some results. So we simulated this so-called parabolic flight, so which is the on-Earth experiment. So the flight is actually going hypergravity, okay, accelerating upwards, then zero gravity when basically simulating the free fall for a few seconds. So for a few minutes. So this is simulating this schedule like 1G and then 1.8G for about 200 seconds, then back to 0G free fall. So you can see that our model captured the heart rate increase and decrease pretty well. So here is a simulation matching result matching the parabolic flight data. So you can see the heart rate increase and decrease matching the actual physiological data pretty well. And also here you can see the heart stroke volume decreased during hypergravity, and then the stroke volume increased under microgravity. So here is a pressure volume loop for the heart chambers, so left ventricle and right ventricle. You can see here that our model predicted really an enlarged ventricular volume under 0G. Especially here you see that for the right ventricle, the pressure and the volume both increased under microgravity. And for left ventricle, basically mainly is the volume of the ventricle increased under to adapt to the microgravity condition. So this is also consistent with the normal observation. So for astronaut spend time in microgravity, the heart is really enlarged due to the effect. Also, our models predicted the heartward fluid shift. You see here the blood, blue line representing the lower body vein blood volume. So you can see that is really decreased, and which is shifted to the upper body vein after the transition. And you see the pressure of the blood of upper body and lower body actually approaching to each other, representing a more uniform pressure gradient. We also try to understand the so simulate the lower body negative pressure. So you can see here is that 1G and suddenly becomes 0G. And then once the LBNP mechanism activated, you can see this heart rate and central venous pressure both restored to some degree. Really, you can see that if you have a negative 30 millimeter mercury LBNP, and is pretty effective in restoring the hemodynamics under microgravity. So the second application is that we also want to study the longer term effects of the the CVSIM model, because in that model is really beat by beat hemodynamics. It does not have any intake and input and output of fluids. So we want to include this water intake and also water exit from the, also want to simulate the long-term effects, which is controlled by the kidney. Okay, so we kind of want to add the renal system model or kidney model into the CVSIM so that we can study the effect of disturbances in longer term. For example, high sodium and low sodium intake and water intake on the effect of hemodynamics. So this is actually an earlier research that is motivated by the high sodium intake effects on the blood pressure. So we kind of include the renal system model, and we know that kidney is a really sophisticated filtration system. So the kidney actually consists of a million of this small unit we call the glomerulus unit, which works to filtrate the water and electrolytes at different locations. Okay, so the artery going in and the filtration goes on. And then after filtration, the blood flow going back through the vein. Now then the excretion is going to be getting out of the body through the urine flow. So in the meantime, kidney also is a long-term control organ that excrete hormones to regulate the blood pressure. So that's the two functionality of the kidney. So that is important for the long-term hemodynamics. So we kind of use modeled the renal system in this green block. So really complex functions, but most of them are either ordinary equations, differential equations, or algebraic equation that is from the literature data. So basically it takes the flow, blood flow from the CVC model and the filtrate this water through this entire process, and then feed back into the venous return into the CVC model. And in the meantime, it also have the hormone concentration modules to control the blood pressure and blood flow. So basically it added another 69 equations. And again, it solves the Runge-Kutta fourth order method. And this time it can be more time step because it's a longer term. And we simulated with a time step of 1 minute. And it can simulate effects of different disturbances in time scale of days. So we can use this kind of modified CVC model to simulate different time scales of hemodynamics. For example, water intake effects in the time scale of hours. Okay. For example, if you take a water in this time window, so we kind of simulated the urine flow rate, okay, responses, and also the mean artery pressure. So this corresponding compared with some clinical data pretty well. We then use this model to simulate the sodium intake on the long-term effect of the hemodynamics. For example, here we simulated some of the clinical results. So here we have a regular sodium intake. Then between the 2 days, we doubled the sodium intake and then restricted the sodium intake in longer term. So what we found is that the different, so here is the plasma sodium concentration matches, and the change matches well with the clinical data. And also here you can see the urine flow matches well, and also different kind of hormone concentration in the blood is also matching the result pretty well. So using that, then we can study the sodium restriction effect on the artery and the heart hemodynamics. Here we studied a restriction of sodium intake. You see different steps of restrictions. So you can see once it was stabilized, the mean artery pressure actually drops to about 1.5 and 5 millimeter mercury in the long term, which matches these clinical data pretty well. And also we are able to show the pressure volume loop of left ventricle work. So the pressure you see here is as the sodium restriction occurs, okay, from 300 millimole per day to 464 millimole per day. You see the loop is actually shifting to this side. Also, the area is smaller, so meaning that the pressure and volume actually decreases, and this total work is also decreasing. Okay, so if you calculate the area, that's the workload of the left ventricle. You see that with the sodium restriction, the workload is actually decreasing, predicted by the model. So it leads to a mitigation of risk of left ventricle hypertrophy in the long term. So that just confirms with some of the common agreement in this clinical field. As a summary of this part, we actually modified the open source lumped parameter model, CVSIM. It turns out to be a very powerful and expandable tool for different kind of physiological and physical phenomena for cardiovascular system. So It can be extended, okay, with different functionality. It can study the hemodynamics in time scale of minutes, hours, days, or even longer. So it's very useful in that sense. But of course, more validations are needed. So more valid physiological data is needed to improve the model in the future. And also the lumped parameter model can also be used as a very good tool to provide boundary conditions, okay, pressure and the flow, the waveforms for CFD, FSI, and experimental study of local hemodynamics in the future. Okay, so that's the first part of my talk. The second part of my talk is that I'm going to going through some of the in vitro cardiovascular flow experiments that we have done, including heart valve, aortic arch, and also left atrial appendage, okay, to study some of local blood flow phenomena. So the motivation here is that in our lab is that we want to study the cardiovascular system hemodynamics, because cardiovascular disease is a leading cause of death. It is about 20% of deaths in 2021 in the United States is resulting from cardiovascular disease. So either atherosclerosis, stroke, arrhythmia, heart valve complications. These are some of the real common situations. The population, the patients with this CVD is also increasing dramatically in recent years. So in all of these diseases, blood flow is a very important role. So either it's because of disturbed the flow pattern or turbulence result, or you know, the in normal warfare stress, all contributed to the modulation the disease pathology of all these diseases. In the meantime, the aortic cardiovascular system disease. So we're going to focus on these really large arteries, heart, aorta, and the large arteries, because the first of all, it's really high Reynolds number. It can be peak Reynolds number can go up to like 5,000 in certain patients, and also it can be very highly pulsatile. So the pulsatility index also very large. The Wolmerslee number is representing the frequency. Normalized frequency is also very high, can go up to like 20. And also it involves a highly complex fluid dynamic, fluid structure interaction and pulsating nature, such as the tricuspid valve of the aortic valve and mitral valve, and also, you know, some of the flow and flow vessel interaction. So in our lab, we actually established a cardiovascular flow simulator, something like this. So we have a programmable pulsative waveform generator. So we can generate any arbitrary user-defined waveforms. So we have the pump head to control the one-dimensional flow. So then we have high-speed sensors, pressure sensor to monitor the pressure, and the test section used to host the models. And then we have compliance and resistance unit to regulate the pressure and volume relations that represented by the, you know, in the cardiovascular, in the system level simulation too. So we want to adjust the pressure volume relation, and then the fluid reservoir to mix the particle seeding, and also serve as the holder for the entire fluids. So this can be used for PIV measurements. So it can be synchronized with the PIV laser and the cameras. And we can do the refractive index matching, because we're currently using a lot of PDMS silicon models to allow the optical access. So that's the main thing we're using right now. So as for the optical flow visualization, we're doing PIV. So particles we're normally using polyamide microspheres. So for refractive index matching is very important, because a lot of this model has a complex circulate cross-section is resulting in optical distortion. So we use water glycerol mixtures that has the about 40% of water and 60% of glycerol, relatively have the same index of a refraction with the PDMs as material. As you can see, the result of the matching. Afterwards, you can see the distortion basically eliminated from the model. So using the pump, we can generate pulsating waveforms, so something like this. So you can see it here, we call this systole, is the contraction phase of the flow. So it's resulting in a larger pressure gradient and flow. And then we have diastole period, which is an expansion of the pump. So it with the one-dimensional valve here, we can actually you see here get to zero flow during the diastole period. So we can study different kind of flow rates and the heart rate. So here's one result, PIV result of the pulsating flow passing the aortic valve. So we're studying how the flow passing these three tricuspid valves looks like, and how that interacts with different structure deformations. So you can see here at different phase of the pulsating flow, we can observe the jet flow, different jet flow patterns. At the peak, you can see there's a jet in the center, and also in the diastole phases, you can see the valve is actually closing, and the resulting non-uniform jet flow towards the end of the systole phase. And then we can also estimate the deformation of the aortic valve, because this is a PDMS is made of soft material. Even though that is material is a linear elastic model, which is not actual real tissue, but we actually can see some of the trend how they deform under pulsating flow conditions. So we kind of measure the area strain, which is the change of this cross-sectional area at the different locations under different flow rate and different phases. So you can see here is that the aortic annulus normally representing the largest strain, regardless of the flow rate, right? So this orange bar shows the area strain of the annulus is the greatest, which is the above, before the aortic valve. And also, we can also see that in the time axis, you can see the area strain of the aortic valve, aortic annulus is actually changing earlier than the peak, before the peak of the flow. We also studied the aortic valve stenosis. We manufactured another aortic valve with a silicon molding, which representing a really, really high electrical Young's modulus. So this one is representing a real severe stenosis calcification, and this original one representing a really mild calcification. Comparing to the real tissue, it's a little bit stiffer, and this one is more severe. So from the PIV result, you can see that the severe aortic valve stenosis actually causes a really strong jet flow because of the narrower opening. So that's comparing to the mild stenosis. So if you compare the velocity profile after the valve, so at the jet exit and the 15 millimeter downstream of the valve, so you can see we compare three cases. So the blue line is the mild stenosis, and the red dashed line is the really severe stenosis, and black dot is actually no valve. Okay, we completely remove the valve. It's only a aortic root without any blockage. So you can see here the jet velocity you see here is really, really high under a severe stenosis case. Okay, so the mild stenosis case is actually pretty comparable with the no valve case. So the severe stenosis caused a twofold increase in the peak general ejective velocity, and also turbulence. So if you compare the turbulence intensity at different locations, you see here that both of the valve conditions result in some turbulence intensity higher than no valve conditions, especially severe stenosis. So resulted really high turbulence after the peak flow. Okay, so it also causes about 3-fold increases in turbulence intensity. So we can kind of evaluated also the normal practical equations used in clinical research, which is the Gordon equation, the Hackey equation, to estimate aortic valve area. So this is a very important equation in practice because for surgeons to doing the artificial valve implantation, they want to estimate what's the area of the stenosis, right? So they kind of based on these really simple equations, the flow rate divided by heart rate and time as the systole and the pressure, mean pressure gradient. And Hackey equation is even more simpler, the heat flow rate divided by the peak to peak pressure gradient. So we evaluated under different heart rate. You can see that it's actually, we found that it's actually also related to the heart rate, right? So it's the aortic valve area, you estimate from this equation, actually you see here, Gordon equation give you a decreasing trend as the heart rate increases. And the Hackey equation actually give the reverse trend. So it's kind of very important also to considering the heart rate in the practice. So so as the heart rate increases, the Gordon equation tends to underestimate the area for the stenosis, and the Hackey equation tends to overestimate the aortic valve area. So the second topic type of research we've done is the aortic arch hemodynamics. So we focus on the deformed aortic arch, which is after after the surgery of coarctation of aorta. So coarctation is basically narrowing aortic arch. So that's normally in congenital heart disease, which is a lot of babies born with these kind of conditions. After they do this, the surgery to remove this section, a lot of patients actually develop different kind of deformations of aortic arch. So one of it is really sharp, we call it Gothic arch. The other is Romanesque, which is really round. So these two type of name is from the Roman architecture styles, right? The European architecture styles. Gothic is really high and tall and sharp, and Romanesque is really round arch conditions. So these different deformation will result in different hemodynamics. So what we wanted to do is to review the flow structures. So we did a PIV, tomographic PIV in this problem. So you can see here, this flow is going from the right to left. Okay, so you can see in the round Romanesque model here, the model is the flow is really pretty uniform, okay, in the cycle. And while in the Gothic is large flow separation, and stagnation occurred. So on the top you can see the flow stagnation. So almost zero velocity near the top, and then flow separation is occurring around this sharp curvature. So we also collaborate with the CFD simulation here. See here the CFD results matches the PIV pretty well. And one of the interesting feature here is because of this arch, it has a secondary flow motion due to the centrifugal force of the flow. So we cut the top here. We look at the cross section at the top. So here is a CFD simulation of the secondary flow. You can see here. Here you have a regular secondary flow around a normal circular pipe. See the vortices developed during this cycle is pretty uniform. But for Gothic result, you can see here is it's an irregular, abnormal secondary vortices, is smaller in size and also stronger in magnitude towards the bottom. So here we compare these results, CFD and tomographic. You can see here the velocity in the Gothic aortic arch is really concentrated near the bottom. So the top is really low velocity, and also the vortices is irregular and concentrated near the bottom. Okay, and then the normal Romanesque model is you have a regular secondary flow structures. And from CFD, we also able to simulate the wall shear stress under these two conditions. You can see here the Gothic aortic arch really resulted in a large non-uniform wall shear stress distribution. You have really high wall shear stress here and low wall stress because of flow separation and stagnation. So the large variations of the wall shear stress normally result in high risks of cardiovascular complications in these patients. The last topic I want to present is the related left atrium and appendage. So left atrium is a really sophisticated chamber of heart that has not received so many attentions from the study, from this field of study. So because the left atrium is above the left ventricle, it's a heart chamber that supplies blood to the left ventricle. So there is a four inlet. So four inlet is a pulmonary veins. So the blood from the lung actually going into the left atrium, and the mixing here and then pushed, sucked by the left ventricle each cycle. So it has one outlet, and here is a valve of mitral valve. They're regulating the one-dimensional flow. So it's a very important chamber because a lot of patients actually develop disease in these kind of chambers. One of the most common disease is arrhythmia, with atrial fibrillation. Atrial fibrillation is very, very common, and is caused by the irregular electrical signal in the chamber wall, and causing that the left atrium is not pumping regularly, but instead is actually a irregular electric signal, so the pressure basically dissipated. Okay, so it do not have the regular waveform. So it affects more than 5 million patients in the United States alone. So under this kind of situation, because the blood flow is not normal, there is a one pouch structure in everybody has this left atrium appendage. So there's a small pouch here. So if the blood flow is not normal, then there's a tendency to develop a blood thrombosis right here in the left atrium appendage. So if that thrombosis travels to the circulation, it can block the brain circulations and cause a stroke. So that's a really risky situation. So a lot of patients developing atrial fibrillation actually will have this appendage blocked or removed through surgery. So in our model, we kind of want to study what kind of flow condition will change the pouch, the flow condition in the pouch. In the meantime, we're also trying to study the flow patterns in the left atrial chamber, which is almost nobody has done this before. So, but which is still ongoing research. So first step, we kind of simulated this kind of flow using a simple flow past a deep cavity model. So we built this two-dimensional cavity. So here we have a flow, pulsating flow through this chamber. Now we have this deep cavity, rectangular cavity, 1.5 aspect ratio. So we simulated in the different kind of Reynolds number and Walmers numbers representing the typical range of the left atrium flow. So you can see that the waveform, if you normalize it, representing similar waveforms. Okay, so flow is going in the systole, acceleration, deceleration, and diastole is almost zero because of the flow valve. So here is the result of the PIV result of the peak at the peak systole, which is the maximum jet velocity here. You can see here at different Reynolds numbers, these vortex patterns at the peak systole is actually different. So here you can see if the Reynolds number is small, the vortex is actually just developing right here and traveling across its orifice, right? because the Reynolds number is small, it doesn't have, it's not strong enough. It's still traveling at this space. But if as the Reynolds number increases, you can see here that the vortex is already shedded and traveled and the impact on the rare surface of these cavity. We also studied the different Wormers number, which is a frequency. So you can see here again at the peak flow, the Wormers number of the main flow increases, meaning that the pulsating flow frequency is faster. So you can see that there is also a main difference here because the main flow is changing so fast. And see here these leading edge vortex has no time to develop and travel. So you see as it increases the peak at the same Reynolds number, you can see the vortex location, the development is different in this cycle. So one major question we have is what is kind of flow patterns at each of the end of the cycle? Because that is when it matters when the thrombosis tends to occur. So we kind of plotted all the cases at the end of cycle. So basically each of the pulse at the end of the phase, we have 10 phases. So at the end of the phase, what does the flow pattern looks like? So you can see we arrange this in the increasing Reynolds number, increasing Wormers number. So from here we can also we calculate the Strohel number, which is basically a product of the Wormers number and the Reynolds number. Okay, we can basically conclude. You see here that the strength of the flow at the end of the cycle is actually mostly dependent on the Wormers number. So which makes sense because the faster the flow changes, the less time the vortex dissipate, right? So there are going to be more flow strength, vortex strength towards the end of the cycle if you have a higher Wormers number. But if you look at the flow patterns, you can see here these flow patterns normally depends more on the Strohel number, is a product of Reynolds number or Wormers number, not on the Wormers number alone. So you can see the Strohel number is really, really small. You build this really nice vortex system in the deep cavity. So again, if you have a longer, deeper cavity, then you have more than 2 vortex. But here you have this 2 counter-rotating vortex in this case. But if you have a larger Strohel number, you can see here because the vortex basically have no time to travel into the orifice, so it doesn't even go into the cavity. So the cavity flow is not affected at all by the vortex. So we can conclude that the large Strohel number resulted in no in-cavity vortex system, and smaller Strohel number resulted in a really nice two vortex system. Okay, so if you really want to enhance the kinetic energy in the flow in the cavity towards the end of the cycle, then you want a high Wormers number as well as a high Reynolds number, which give you a relatively lower Strohel number. Okay, so that's our conclusion. And here we plotted the mean kinetic energy in the cavity against the Wormers number and Reynolds number as well as Strohel number. You can see this nice trend under different Wormers number. You see here as the Strohel number decreases, the kinetic energy all increases inside the cavity. Lastly, there's some ongoing research that we're doing some tomographic PIV measurements on the real, the model left ventricle model. So the challenge here is that this chamber is really, really complex. It has 4 inlets, the jet impact each other, and then it also irregular geometry. Is the flow is really complex too and turbulent. So we want to do the tomographic measurements of 3-dimensional flow in 2 directions like this because we are limited in space of the volume illumination. So here is some videos showing the actual pumping of the left ventricle. Here, just a reminder here that we don't have the mitral valve constructed between the left ventricle and the left atrium model. So, so you see here the flow coming into the chamber through 4 inlets. And we're simulating the left atrium waveform, which is double peak. The first peak is by the left ventricle suction. The second peak is its own pumping. So we simplified it to two waveform in inlet boundary condition. So here you can see that the flow is really, really complex, as you suggested by the dye illumination here. You see here, really swirling and turbulent conditions and pulsating conditions. So the boundary condition is generated by the CVSIM model. So this is a double peak of aortic valve. So the first peak we called the E wave is caused by the suction of the ventricle. The second is the A wave by the pumping of the left atrium itself. So this is representing a healthy left atrium. So in the atrial fibrillation cases, the patients will lost the ability of the A wave, which is its pumping function is lost because the electrical signal is irregular. So the red dashed line is the patient condition AFib flow, which is only one wave. So we simulated this in the posterior view. So you can see the tomographic measurements actually give us a pretty good view of this vertical big vortex system in the cycle. So this is a normal healthy waveform. So you can see this double peak. Okay, the red color appears twice in the cycle, and a continuing vortex inside this left atrium. This is the AFib waveform. You can see here is only one wave, and then the flow velocity becomes very low for the rest of the time in the cycle. And if you compare this magnitude, so at the different time step, so you see that the healthy ones get really, really uniform high velocity throughout the ejection most of the time, but the AFib really lacks of the high velocity for majority of the cycle. So it can cause problems. So if you compare this as time step, the kinetic energy distribution in this slice, you kind of compare to see that AFib really have low kinetic energy for most of the time during the cycle. So it can cause the blood stasis in the chamber, also the aortic appendage. So that might be contributing factor for the stasis and the blood thrombosis to occur. So just a summary. So we kind of reviewed some of our work in the local flow visualization for the different kind of problems. As you can see, most of the problems show strong pulsatility, three-dimensionality, fluid structure interaction is really complex. So that demands a high quality flow measurements because there's really a lack of validation database for CFD simulations. It's really complex flow, so there's a lot of chances for future computational and experimental simulation of these problems. And also combining the system level mathematical modeling also helps with the in vitro experiments and the CFD because it can provide some of the boundary conditions that we are not able to get normally easily from the clinical data. Acknowledgement, I'd like to acknowledge all my students contributing to the works that I presented today. So some of them are already graduated and some of them are current PhD students. And also want to give special thanks to my colleagues and collaborators in my department, Dr. Jordi and Dr. Susan in my department. So with that, I want to conclude today's talk. And if you are interested in, you can contact me at this at this email, and also this is my personal website. So you're welcome to contact me for any questions, and we can discuss also for future collaborations too. Thank you very much.
Sorry. Hello. And thanks for your interesting talk. It's time to ask questions. Any questions? Any questions? Okay, Professor, I have some questions. And I see you did some PIV experiments, including planar PIV or three-dimensional PIV. So, but I think the material of your chamber or the tube is soft. How can you keep the same shape during different experiments?
Well, we don't keep the shape as same, so it actually deforms. Yes.
It actually deforms, but your result actually should be the phase averaged results, or just the phase average. Yes. So if the shape is changed, I mean, maybe the results should be, how can you get the phase average results?
Well, it changes, but it's an elastic change. So for phase locked simulations, most of them are the same geometry. So
okay, yeah.
So yeah, it deforms during a cycle, but it's a repetitive pattern. So
yeah, okay, I see.
Yeah, we phase lock at a certain time, so it will be the same geometry. So
okay. And someone says on the chat, can you see it? Meeting chat. Someone ask a question. Why TT?
Important and highly unsteady. Well, yeah, I mean, strictly speaking, why not vorticity? Yeah, I mean, vorticity is important in a highly vertical flow. Yeah, investigate vortex structures. Yes, that's true. But turbulence also important because of its physiological relevance. So a lot of the pathology and the thrombosis and all those diseases actually develop under certain renal shear stress and high turbulence conditions. But to be strictly speaking, so far some of our heart valve turbulence, so-called turbulence, is not a real turbulence, because for heart valve, the PIV we're doing only for those studies, we're only doing two-dimensional and also phase locked. It's not a time resolved measurement, so it's not really strictly speaking, it's not turbulence intensity, but rather a standard deviation, the fluctuation of the velocity in that flow field. So
thanks, Professor. Any more questions? Any more questions? Okay, good, Professor. Thanks you again for your interesting talk. And if someone have more questions, please keep in contact with us or keep in contact with Dr. Zhang. Thank you again. And
thank you very much.
Thanks for listening to today's seminar, and I hope we can see you next week. Have a good day.
Okay.
Bye-bye.
Bye-bye. Thank you.